Okay, so just to sort of recap where we're at relative to internal flow, we have talked a little bit about the correlations that you would use, correlations to get the pressure gradient and the pressure drop, so the local and the average friction factor, correlations to get the local and the average heat transfer coefficient, so the local and the average Nusselt number, and this is sort of what they depend on, those correlations. And we specifically talked about how you would access a library in EASE that has these programmed in them, but there's nothing magic about that. You can obviously access these however you like, but this is the functional dependence. And then the other thing we talked about just last time was this idea that it's not enough to get like a heat transfer coefficient in order to solve an internal flow problem. You also have to think about an energy balance. You have to think about how the mean temperature of the flow is changing as the flow moves through the duct. So today let's try to use these ideas to solve an internal flow problem. So here's the problem that I came up with. So this is a current lead. So if you're going to pass current to a superconducting magnet, for example, even if it's high temperature superconducting magnet, you still have to pass current from room temperature down to a relatively cold temperature, below 100 Kelvin. And that's a lot of current, and this metal that you're passing it through isn't superconducting, so it has some electrical resistivity, and therefore it tends to get hot. So there's different ways of cooling these magnet leads. One is just conductively cooling them. So you cool the cold end, and you hope that the rest of it doesn't get too hot. We talked about that, I think, before in a different example problem. More common is actually you do what is called vapor cooling. So you vapor cool the current lead. So in that kind of an arrangement, what you do is you actually run vapor through channels in the lead, right? So here's a situation where we have a current lead that's in the shape of a cylinder, right? So the current is flowing through the wall of the cylinder. The wall is actually, this isn't to scale, obviously this wall is pretty thick. The current lead is actually more material than it is channel if you look at these dimensions. So here's my cylinder that forms the current lead, and the vapor flows through the center, and that vapor then is going to actually help cool the current lead and keep it from getting too hot. The vapor is typically generated by boil off of whatever cryogen you have submerged your superconducting magnet in. So in this particular case, we're going to assume that we have a Dewar, and it's filled with nitrogen. So there's a liquid nitrogen bath basically somewhere in the Dewar. And then as there's heat leak to that bath, or there's heat coming through the magnet, or there's heat being generated by the operation of the magnet, so all these different places that it can gain heat, it's going to boil off. And the vapor has to get out. And so what you do is you give it, a limited number of paths to get out, and one of those paths is to travel through your current lead. So the vapor that's going through my current lead is actually coming from the boil off of the cryogen. And typically you can't pressurize these Dewars very much. They're not really pressure vessels. So we're going to allow our Dewar to get pressurized to 4 kilopascals. So the pressure inside of this Dewar, which is the pressure at the inlet to this current lead, is 4 kilopascals higher than the ambient pressure that sits outside. So that 4 kilopascals is a pressure difference that's forcing flow through our channel, through our duct, basically. All right, so that's the situation. Some dimensions, I guess. One is, what's the dimension of the channel? So this cylinder is 1/4 of an inch outer diameter. That's the conductor, outer diameter. And the channel itself has 0.1 inch diameter, so the conductor has a 0.1 inch inner diameter. So this out here, this gray area is all material. This is where the current flows. And this white area here this is open. This is where the nitrogen vapor is flowing. The current lead is 18 centimeters long, so that's the length of our duct. Let's see, the vapor is entering here at whatever the saturation temperature is at, 100 kilopascals plus 4 kilopascals, so about 104 kilopascals. So that'll be something like 78 Kelvin is the temperature entering here. We're going to push 1,000 amps through this current lead. We're going to assume the conductor is made of a material with constant properties. That's a pretty bad assumption, actually. A lot of times when you're dealing with cryogenic situations, you'll find that the properties vary quite substantially, but just for this problem, as a first cut, we'll assume the conductivity, the thermal conductivity is 75 watts per meter Kelvin, and the electrical resistivity is 1 times 10 to the minus 8th ohm meter, right? So that's a material property. And the question is, I think, pretty obvious, which is, how hot does the current lead get, right? I mean, in the end, as long as your current lead doesn't melt, you're probably okay. So how hot does it get, and where is it the hottest, right? So those are questions we'd like to answer. Let's see if I can switch over to my EASE program here. So here's the EASE program, and if you look up here at the top, everything up here is basically all the inputs, right? So these are my dimensions. I converted everything to base SI units. Let's see, I'm using nitrogen. I have to use nitrogen and not N2 because I'm going to rely on the fact that it's boiling. So I want some properties right on the vapor dome, right? And N2 is an ideal gas model for nitrogen. I need the complete real fluid model of nitrogen, which is nitrogen. Ambient pressure is 100 kilopascal. The doer is pressurized to 4 kilopascal. And then the inlet temperature, so this is the temperature of the stuff entering the channel, is going to be the saturation temperature, so X equal 1 at this pressure, right? So if I solve, I should find that TFN is, right around 77, 78 Kelvin, right? So pretty cold stuff entering my current lead. All right, so that's the problem, right? Just like with any problem, we have to think of some ways to simplify it so that we can attack it. So a couple of simplifications that I'm going to make, and one of them we'll come back and look at the end. One simplification I'm going to make is I'm going to neglect axial conduction along this current lead, right? So I'm going to neglect the fact that there's axial conduction, there's conduction in this X direction along the current lead, and see where that takes me. And then at the end, I'll come back and look at whether that was a good assumption or a bad assumption. And I'll do that with thermal resistances because that's always how you look at these assumptions. The other assumption I'm going to make is that just like I'm modeling the conductor with constant properties, I'm going to model the fluid as having constant properties, right? So two assumptions that could be relaxed to make the model a little better, but that's the way we're going to go for now. So let's see what the first assumption tells me. So if I am ignoring axial conduction along the current lead, so here's the current lead, then when I do a control volume that includes a differential slice of this current lead in the X direction, let's see, we're going to do an energy balance on this control volume. We're going to say in equals out plus stored. Well, stored goes away because this is a steady state problem. There is no heat transfer through this surface or this surface if I'm ignoring axial conduction, right? So my only in then is whatever ohmic dissipation, whatever thermal energy generation I have inside of this control volume. And that's going to be the resistance of the control volume, the electrical resistance of the control volume relative to current. So that electrical resistance is the resistivity times dx. Dx is the distance I have to move the current divided by the cross-sectional area of the conductor material. So that's electrical resistance times current squared, so I squared R, right? This right here, this ACC, this is pi over 4 times the outer minus the inner diameters each squared, right? So this is the area, if I go back, this is the area of this material. This is the area that the current has to flow in. All right, so that's an in. And then an out is, well, the only way this material is getting out, if I assume this outer surface is adiabatic, is to the flowing vapor, right, to the vapor in the center. So that's a heat flux at the surface of my duct times the perimeter times dx, right? That's this surface area here. This perimeter I'm talking about is pi times the inner diameter of the conductor, right? That's this, if I go back one, that's this perimeter right here that is wetted by the vapor as it flows. So in equals out, right? If I come up here and just write my control volume, in equals out, then I can cancel out these dx's and solve for the heat flux, and this is my equation for the heat flux. So the heat flux, if I make the assumption that there's no axial conduction, the heat flux on the surface of my duct is constant. So that's the boundary condition. That's the thermal boundary condition that I have for this problem, assuming that that assumption is right, right? The other way I could go at this point is say, well, there's so much conduction. This is so conductive in this direction that the temperature is constant. Actually, that there is no temperature gradient in this direction because that conduction is so strong, right? And then I would have a different limit, which would be that the duct experiences a constant surface temperature, right? So, we have to go one of these two ways. And again, which of those is more right has to do with what are the resistances, right? What are the resistances involved? So at the very end, we'll go back and look at these resistances and decide whether or not, this is the right way to go or the constant surface temperature limit is the way to go. This is the one we're going to use for now. So I can do these calculations. Go back to my ease model. So this is the cross-sectional area associated with the conductor. This is the area through which the current has to flow. That's the perimeter exposed to the vapor. And then this is that equation we derived for the heat flux. So the heat flux experienced by the current, by the vapor as it flows along there is 47.1 kilowatts per meter squared. Right, so that's the heat flux on the surface of my duct. All right, so that's helpful. What's next? So the other assumption that I decided to make is that I'm going to use constant fluid properties, right? So obviously, as the vapor is being heated and losing a little bit of pressure, temperature and pressure are changing, so these properties are going to change a little bit, and I'm going to ignore that for this model. And again, the way we would decide at the end whether that was a good assumption or a bad assumption is we come back and look at how much are these properties changing, right? Are they changing so much that the behavior at the cold end and the behavior at the warm end will be very different, right? But for now, this is an assumption we're just going to make. So I have to use some constant properties. So what's the best properties to use if you're going to use just one value of the properties? Well, it would be the value evaluated at the average pressure and the average temperature, right? So the average pressure is the inlet temperature plus the outlet temperature divided by 2. So this is, in this case, to be the ambient temperature plus half of that pressurization, right? So I guess this would be like 102 kilopascals. This pressure dependence is pretty small because the pressure is not changing much. The average temperature would be the inlet temperature, which is like 77.6 Kelvin, plus the outlet fluid temperature divided by 2. And here we do run into an issue, which is I don't know what that outlet fluid temperature is, right? So this is a case, like in almost every heat transfer problem, where you're trying to evaluate properties using temperatures that you don't know until you actually solve the entire problem. And the best way to go in any time you run into this kind of a situation is not to wait until you solve the entire problem to hit solve, but rather to, at this point right here, make a guess for the outlet temperature, or make a guess for the mean temperature, and proceed using that guess. And when you're all done, then once everything is working okay, you can solve for this outlet temperature and adjust this temperature that you use to get the properties, and everything should converge much more dependably than if you tried to do this all in one fell swoop, right? So let's look at this. So if I go to my ease file, what did I do here? I assumed that the average temperature was 200 Kelvin, right? You can see later on I'm going to put this equation in once I know the outlet temperature and get rid of this equation. But for now, let's assume the average temperature is 300 Kelvin, and then we'll just calculate all of these fluid properties, right? So this is C, and viscosity and conductivity and density and the Prandtl number. Okay, so that's where I'm at. The next thing I need to do is think about, what is the mass flow rate through this duct? So this is a pretty typical situation where I'm not actually given the mass flow rate. What I'm given is something about what am I hooking the duct up to, right? In this case, I'm hooking the duct up to a pressure source, right? I know the pressure here and I know the pressure here, and then based on that pressure source, that's going to dictate how much flow goes through the duct, right? The duct has some hydraulic resistance, and based on what the hydraulic resistance is, that's going to dictate how much flow goes through it. In your homework, and in actually almost every problem you'll do, you'll hook a duct up to something more like a pump, right? Where the pump will give you a pressure rise across the duct, and that pressure rise isn't just a constant. It depends on the flow that you're drawing from the pump. And then, your duct is going to give you a pressure drop that isn't constant. It depends on how much flow is going through your duct. And so you have to make those two components line up, right? You have to make sure that the pressure and flow you're asking your pump to give you match the pressure and flow that your duct requires, right? And so that's certainly some kind of an iteration, and that's what we'll do next.